Swayam Prabha. Digital India. Educated India.
Welcome to Organic Chemistry Paper 3. In Unit 4, we are studying about alkaloids. In the lecture 4, we are going to study about structural elucidation and medicinal uses of a few alkaloids. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this session. We will start with the structural elucidation of hygrine. Then we will also study about the synthesis of hygrinic acid and hygrine. From that, how we can reduce the structure of hygrine we will study. We will also study about the biosynthetic process by which hygrine is synthesized from ornithine. Later on, we will study about structural elucidation of nicotine. So here we will be looking at what is the structure of nicotinic acid, and from nicotinic acid how we can prepare nicotine we will see, and we will also look at some of the synthesis of nicotine. We will look at medicinal importance of various alkaloids. We will study about nicotine, hygrine, quinine, morphine, cocaine and reserpine. In this session, we are going to look at structural elucidation and medicinal uses of a few alkaloids. We are going to look at the structural elucidation of an alkaloid named hygrine. So, the molecular formula of the hygrine is given as C8H15ON. So, this is having one nitrogen. So, that is why this is a alkaloid. This is one of the cocoa alkaloids. That means this compound was actually isolated from cocoa leaves, and this is soluble in dilute acid, but it is insoluble in aqueous sodium hydroxide, and this does not react with the benzene sulfonyl chloride. So, this shows that there is a tertiary amine that is present in this particular alkaloid, and it also gives a phenyl hydrazone derivatives with phenyl hydrazine. That shows the compound contains a carbonyl unit, and the chromic acid oxidation gives a hygrinic acid with a molecular formula C6H11O2N. So, we can conveniently put it like a hygrine is having the molecular formula C8H15ON, and this does not react with benzene sulfonyl chloride. So, this shows the presence of tertiary nitrogen. This gives a phenyl hydrazone derivative when treated with phenyl hydrazine, which shows the presence of carbonyl unit C double bond O, and chromic acid oxidation gives hygrinic acid. So, based on that, we are going to deduce the structure of hygrine. So, from the molecular formula of hygrinic acid, we can actually identify there is only one double bond equivalent. So, that means we can have either open or a cyclic structure. Let us look at the various possible ways how we can draw the structures. The first one is a cyclic structure. So, this is a 6-membered nitrogen unit because we have a tertiary nitrogen. So, this is the main thing we have to remember, and that benzene sulfonyl chloride reaction shows that there is a tertiary nitrogen. So, we have to look at what are the different ways by which a tertiary nitrogen can be written in a ring structure, because the double bond equivalent is 1. Now, we are going to look at the structure of hygrinic acid and not hygrine directly. So, because this hygrinic acid is obtained from hygrine, so the molecular formula C6H11O2N is the molecular formula for hygrinic acid, and we are going to look at what is the actual structure of hygrinic acid. So, from this we find it out like there is a double bond equivalence 1. So, we do not have to worry about the carbonyl unit that is present in the hygrine now. So, there is an acid unit and there is a 6-membered ring. So, this is one way of writing the structure. Another one, because here again this nitrogen is in the tertiary form. So, if we look at all the structures, we have couple of structures which are tertiary nitrogen. So, this is a tertiary nitrogen. Here again we have a tertiary nitrogen. Here we do not have a tertiary nitrogen. So, here also we do not have a tertiary nitrogen. We only have a secondary nitrogen. So, when we have the secondary nitrogen, then of course, this compound may or may not satisfy that benzene sulfonyl chloride reaction. So, this is a tertiary nitrogen. So, because this is obtained after oxidation. So, that means this acid unit may be present later on. So, let us look at what are the different structures which are possible. And if you look at the 6-membered ring, the next step is the hygrinic acid on dry distillation gives N-methylpyrrolidine. So, this is one of the crucial thing we have to take into account. So, if we look at the N-methylpyrrolidine structure, so this is the structure which is possible for the N-methylpyrrolidine. So, that means the pyridine structure is completely ruled out, because the pyridine structure cannot give a N-methylpyrrolidine type structure. So, from 6-membered ring we cannot go to 5-membered ring on simple distillation. So, this structure is ruled out, and these are structure this and let us say if I put it like A, B, C, D, E and F. So, these are all the different name we had given for the structures. A is ruled out because it is having a 6-membered ring, and if you look at E and F, they have a secondary nitrogen. So, that is also ruled out, and we have now a few other structures left out, which are B, C and D. But D is a open chain structure, so this cannot give N-methylpyrrolidine on dry distillation. So, this is also ruled out. Now, we have only 2 structures. So, between structure B and C, in structure C there is no N-methyl group that is present. So, that means this cannot give N-methylpyrrolidine on oxidation. So, this structure is also ruled out. So, now we are left with only one structure, that is the structure B, where N-methyl group is present. We also have a tertiary nitrogen, and this is having only one carboxylic acid group. Now, we have 2 possibilities, because the carboxylic acid can be present at position number 2, or the carboxylic acid can be present at position number 3. So, there are 2 ways, because both these compounds will actually on heating gives N-methylpyrrolidine. The only difference is, if it is at position number 2, this gives the N-methylpyrrolidine very quickly or very fast, whereas if the carboxylic acid is present at 3 position, the decarboxylation is very slow, or it takes longer time. So, from the rate or the how quickly we can convert this hygrinic acid into N-methylpyrrolidine will tell about the position of the carboxylic acid unit, and it was shown that the hygrinic acid gives the N-methylpyrrolidine very quickly. So, we can say the hygrinic acid is having the structure, pyrrolidine structure as shown here, in which the carboxylic acid unit is present at position number 2. So, the structure of hygrine is confirmed by the synthesis. So, here we start with the 1,3-dibromopropane. This is treated with the sodium salt of the anion of the malonic ester. So, this is the malonic acid. So, there is an anion here. So, this anion reacts with this one, this 1,3-dibromopropane, and one of the bromine is replaced. That means it is a simple SN2 type reaction. So, the anion attacks here and the bromine is lost. So, the anion actually attacks this particular carbon and the bromine is lost. So, we get the condensed product, and this on treatment with the bromine undergoes bromination at this particular carbon. So, this is the most acidic hydrogen, and that is replaced by the bromine atom, and then treatment with methylamine actually leads to the cyclization. So, these 2 bromine atoms are removed, and we end up with a cyclized derivative, and this diester is treated with barium hydroxide, that leads to the dicarboxylic acid, and that dicarboxylic acid on heating very readily loses one of the CO2 group to give the hygrinic acid, and from this structure we can actually see that the carboxylic acid unit is present in the 2nd position. So, this is how we can confirm the structure of hygrinic acid. As we have seen earlier, the hygrinic acid is actually formed by the oxidation of hygrine. Then we have 2 possible structure that is possible, because here again the position we can actually have the carbonyl unit. See, the 2nd position is the place where the hygrinic acid is attached. So, we can have the acetyl unit on the second carbon. So if we look at the carbon side chain, if you put like 1, 2, 3 numbers, so here again you start from 1, 2, 3. So the second position can have the carbonyl unit. This on oxidation, because we are going to break this bond, and that is how we end up with a carboxylic acid here. So that means whether the carbonyl unit is present on carbon number 1 or carbon number 2, we are going to get the same hygrinic acid only. So we have to now find out whether the carbonyl unit is present at position number 2 or at position number 1. So if we take another reaction where the alpha methyl aminobutylaldehyde, alpha here is the methyl unit, so this is the alpha methyl butyraldehyde, because we have 1, 2, 3 and 4 carbon units. So this is a butyraldehyde unit. So there is a methyl group on the nitrogen. So this is the alpha methyl aminobutyraldehyde. This is reacted with ethyl acetoacetate at pH 7. That gives hygrine. So when hygrine is formed, that means here the only possibility is the carbonyl group can be at position number 2 only. So from that we can actually deduce the structure of hygrine. And of course the biological synthesis also had shown that the hygrine structure. So then finally the structure of hygrine is confirmed by the synthesis. So here pyrrole is reacted with methyl magnesium bromide to give the pyrryl magnesium bromide. So the hydrogen is replaced by the methyl magnesium bromide and we end up with the pyrryl magnesium bromide, and this pyrryl magnesium bromide is reacted with the propylene oxide. So when it reacts with the propylene oxide, so this actually attacks this particular carbon and this actually opens up towards oxygen. So we end up with the compound as shown here. So this corresponding carbinol is reduced, that pyrrole ring is reduced to pyrrolidine ring using hydrogen platinum, that is the saturation of this ring takes place, and then a treatment with the formaldehyde finally gives the hygrine structure. So this last step is the oxidation step, that means N-methylation reaction, because this nitrogen is having only the hydrogen. So N-methylation is carried out with the help of formaldehyde. So that leads to the N-methyl derivative, and final oxidation we have the hydroxy unit. So this hydroxy unit on oxidation gives the keto unit. So the final structure of hygrine is obtained after oxidation. Now let us look at the biosynthetic process by which hygrine can be produced. So here are the various steps that are given here. So biosynthetically, ornithine is the starting material for hygrine synthesis. So this is the structure of hygrine, and this loses the carboxylic acid unit. That means the decarboxylation is the initial step that leads to the formation of putrescine. So this is a diamine. This diamine then undergoes a methylation. So one of the nitrogen undergoes a methylation to give the N-methyl derivative, and this then undergoes oxidation to give the corresponding methyl aminobutanol. So this amine undergoes oxidation to give the corresponding aldehyde unit, and this undergoes a cyclization, so that we end up with the carbinol amine as shown here. So this is the cyclized derivative, and this loses water molecule to give the N-methyl delta 1 pyrrolium cation. So this is a very crucial intermediate, and once this intermediate is formed, this reacts with the acetyl CoA. Two-step addition actually happens. First one acetyl CoA unit is added, so that is how we get this particular unit in this molecule, and then the second acetyl CoA unit is added, so we get the corresponding structure here, and this is actually, this acetyl unit is lost, and then we end up with the ester as shown here. So this is a beta keto ester. So this is the final product before hygrine is actually formed. So, this is then converted into hygrine. That means this beta ketoester is hydrolyzed to give the corresponding hygrine derivative. Let us move on to the next compound which we are going to see is the nicotine. So, the structural elucidation of nicotine we are going to see. The molecular formula of nicotine is C10H14N2. This is one of the tobacco alkaloid. Actually, this is isolated from tobacco leaves. It is soluble in water, and this also does not react with benzene sulfonyl chloride. That means there is a tertiary amine present in this particular compound, and chromic acid oxidation gives nicotinic acid, and Hershey's-Meyer method shows the presence of one N-methyl group. So, these are all the clues or the information we already have. From this we are going to deduce the structure of nicotine. So, the nicotine on treatment with benzene sulfonyl chloride, there is no reaction. So, that means there is a tertiary nitrogen present in this particular compound is confirmed by that, and the Hershey's-Meyer method shows that there is a N-methyl group. There is one N-methyl group present in this compound, and although there are two nitrogen, so that means out of the two nitrogen, one is having a N-methyl unit and another may be a tertiary nitrogen. We have to see what is the nature of the tertiary nitrogen. And nicotine on oxidation using chromic acid gives nicotinic acid. So, let us start from the structural elucidation of nicotinic acid. From this we will move on to what is the structure of nicotine. So, from the molecular formula of nicotinic acid, that is C6H5O2N, few cyclic structures are possible. Here the double bond equivalent is 4. So, based on that 4 double bond equivalent, we are going to deduce what are all the different structures that is possible for nicotinic acid. So, one is a 6-membered structure, another one is a 5-membered structure with 3 double bonds. So, here we have the 1, 2, 3 double bonds are there and one cyclic structure is there. So, the double bond equivalent 4 is there, and here we have 2 double bonds, one cyclic structure and one exocyclic double bond. So, here also we have 4 double bonds. So, the double bond equivalent is actually satisfied, and it was shown that this compound nicotinic acid is a isomer of pyridine carboxylic acid. So, this is one of the isomer of pyridine carboxylic acid, it was shown. Now, we have to find out. So, that means this structure, the exocyclic double bond structure is ruled out. Now, the structure is going to be a pyridine, but we need to find out where is the carboxylic acid, whether the attachment is at position 2 or at position 3 or at position 4. That is what we have to see, the nicotinic acid structure. So, the 7,8 benzoquinoline is converted to pyridine 2 carboxylic acid, and 5,6 benzoquinoline is converted to pyridine 3 carboxylic acid, and the isoquinoline is converted to pyridine 4 carboxylic acid. So, these are all the different starting materials from which these 3 different carboxylic acids are actually formed. So, from this we are going to deduce what is the nicotinic acid's position. How do we deduce the structure of nicotinic acid? So, these 3 compounds were later on confirmed with the product that is obtained by the nicotine. So, nicotine was oxidized to one particular acid, let us say this is acid A, and we have 3 different acids that are obtained from 3 different starting materials, and we exactly know what is the position of the carboxylic acid unit in all these 3 compounds. So, now a comparison was made between this nicotinic acid with all the 3 acids. So, this is pyridine's 2 position, pyridine's 3 position carboxylic acid and pyridine's 4 position carboxylic acid, and by the comparison it was found that the nicotinic acid was matching with the pyridine 3 carboxylic acid. So, from the melting point comparison and other comparisons, it was found that pyridine 3 carboxylic acid was actually nicotinic acid that was obtained. So, from that we now know exactly the position of attachment. So, that means the pyridine unit and the carboxylic acid unit are attached at position number 3. So, this was deduced from the comparison studies. Now once the comparison was done, the next one is we are going to find out the pyridine's side chain, because we know this position was the one which was actually converted to the carboxylic acid position. So that means the 3 position attachment is already confirmed. So we have a pyridine ring and some substitution at this position. Now we are going to find out what is this C5H10N unit. So the presence of N-methyl group rules out the piperidine moiety. So we can look at what are the different structures possible. We have a C5 unit. So C5 unit is actually attached here. So that means if we are going to have a N-methyl unit, so here 1, 2, 3, 4, 5. So there are 5 carbon atoms and 1 nitrogen is there. Here we have 1, 2, 3, 4 and 5 here. So that means for the C5 unit, this structure is completely ruled out, because we have a N-methyl group that is present, because Hershey's-Meyer method has shown that there is a N-methyl group, but in pyridine we do not have the N-methyl. So in other words, the N-methyl will have to be present only in the side chain. So that means the piperidine structure is completely ruled out, because this cannot have a N-methyl unit. So the probable structure is only the N-methyl pyrrolidine type unit. So here only we have the N-methyl unit, which actually matches with the nicotine's side chain. Nicotine on distillation with the lime actually gives pyridine, pyrrole and methylamine. So this clearly tells that we have a 5-membered nitrogen heterocycle that is present here. In other words, pyrrole or the pyrrolidine unit is the one that is present in nicotine. So that is confirmed by this particular reaction. And of course, formation of N-methylamine also confirmed that we have the N-methyl group. This is also confirmed by the Hershey's-Meyer method. So now the next question is, what is the attachment of this particular unit, that is pyridyl unit, the pyrrole unit to this pyridine unit. So this pyrrole can be attached at position number 3, or this can be attached at position number 2. Between the pyridine and these two groups can be attached at 2 different positions. Now we have to find out what is the actual attachment position. So far we have confirmed that the C5 unit is actually the pyrrole type unit, and there is a N-methyl that is present here. So this is confirmed, and now we have to only confirm the attachment of this group. So how are we going to find out? There are a couple of experiments which are carried out to find out that. The first one is the nicotine was treated with the bromine and acetic acid. So the whole molecule, the nicotine, is treated with bromine and acetic acid, and it gave a per-bromo derivative, and this per-bromo derivative on treatment with sulfuric acid gives dibromo-nicotine, which on heating at 130 to 140 degree with sulfurous and sulfuric acid gave 3 different products. One is an oxalic acid, another one is a methylamine, and 3-acetyl pyridine. So these are all the 3 products that are formed. So this is a 2-carbon unit, let us say, because pyridine unit we already know. So we are going to find out the C5 unit. So how the C5 unit is present? We have a 2-carbon unit here. We also have a oxalic acid that is formed. So that means we have another 2-carbon unit and N-methylamine. So there is 1 carbon unit. So we have a combination 2C plus 2C plus 1C combination we have now. And nicotine when treated with bromine in the presence of HBr. So we are using a different brominating agent, because in the previous case we used bromine and acetic acid. Now we are using bromine and HBr. So this gives a different dibromo-nicotine derivative. This dibromo derivative on treatment with aqueous barium hydroxide at 100 degrees centigrade gives 3 different products. The first one is a nicotinic acid. Second one is a malonic acid. The third one is a methylamine. So 3 different compounds are formed. So here we have 1 carbon unit. In the malonic acid, we have a 3 carbon unit and we have 1 carbon unit on the methylamine. So, another combination is 1 plus 3 plus 1. So, the C5 unit is actually formed from 1 plus 3 plus 1 combination. So, this tells very clearly we have a 4 carbon unit that is attached to the pyridine unit and 1 carbon is present on the nitrogen. So, this is actually confirmed. So, that means whatever may be the combination, it has to be the 4 carbon is directly attached to the pyridine unit and one of the methyl group is attached to the nitrogen. So, this is confirmed now. So, if we look at the different bromination products, so we have the nicotine, starting material is here. So, this nicotine on treatment with bromine and acetic acid gives a bromo derivative as shown here. So, this is a dibromo derivative, and this on treatment with the sulfurous acid and sulfuric acid gives, this is the bromine, this is the nicotine, and this is the pyridine unit and 1 carbon. So, these two, and there is also another carbon. So, these 2 carbons combine together to give the acetyl unit as shown here, and these 2 carbons actually form the oxalic acid part, and this N-methyl unit actually forms the methylamine part. So, this is one way of breaking the molecule, and in the other case what happens is the pyridine unit and only 1 carbon are joined together to give the nicotinic acid, and we have 3 carbons 1, 2, 3. These 3 carbons together forms the malonic acid, and this N-methyl unit actually gives separately the N-methylamine derivative given here on oxidation. So, by that we actually can work out what are all the possible ways the attachments are present. And finally, it is confirmed by the reactions, other reactions, because nicotine behaves like a di-tertiary base because it undergoes addition with 2 methyl iodide. So, that means there are 2 tertiary nitrogens are present. We already know one is a pyridine nitrogen. So, the second one has to be the side chain having the N-methyl unit. So, this also we have already confirmed. So, the N-methyl unit is actually present here as shown, and then, so here in this nicotine the N-methyl unit is present. So, it consumes basically 3 moles of hydrogen during reduction. So, that means the pyridine has 3 double bonds. So, these three double bonds only undergo reduction. That means pyridine is converted to piperidine unit. So, that means whatever is the side chain has to be a saturated one, and nitrogen should also be cyclic in that system. So, it is a saturated one, that is also confirmed. Then formation of the hygrinic acid from nicotine, that is methyl iodide addition and potassium ferricyanide and chromic acid oxidation, all these steps leads to the conformation of a pyrrolidine unit. So, the hygrinic acid formation also confirms that this particular unit is present in the nicotine. We already had deduced the structure of hygrinic acid. So, this becomes much easier for us to confirm the structure of nicotine. So, the final structure of nicotine is confirmed by the synthesis. So, starting from succinimide, the electrolytic reduction gives 2-pyrrolidone. One of the carbonyl unit, that is, this is the amide unit. So, this one of the carbonyl is reduced to give the 2-pyrrolidone, and this 2-pyrrolidone was converted to the N-methyl derivative by treatment with dimethyl sulfate and sodium hydroxide, and this was again treated with sodium ethoxide, which is a strong base. So, what it does is this is the most acidic hydrogen. So, the base abstract a proton from this one, and this particular anion actually attacks this electrophilic carbon, and this actually moves towards here. So, we end up with the corresponding intermediate as shown here. So, the condensation actually takes place at this position adjacent to the carbonyl unit, and then this on treatment with HCl at 130 degree centigrade undergoes a ring opening, and we end up with a carboxylic acid unit. So, this this particular bond breaks and we end up with a carboxylic acid unit here, and this on heating undergoes decarboxylation. That means this particular carboxylic acid unit is lost, so we end up with the keto compound as shown here, and this keto compound was reduced using zinc dust and ethanol and sodium hydroxide to the corresponding hydroxy unit. So this was then treated with hydrogen iodide at 100 degrees centigrade to give the corresponding iodo derivative. So once the iodo derivative is there, this iodo derivative undergoes cyclization with this NH unit, and in the presence of sodium hydroxide, this undergoes cyclization to give nicotine. So starting from succinimide, we can actually prepare nicotine by the steps of reactions given here. So this confirms the structure of nicotine. And of course, there is also another method by which nicotine can be synthesized. The plus or minus nicotine can be synthesized via Hofmann-Loeffler reaction. So this is basically a radical cyclization method. So starting from the aldehyde, pyridine carboxaldehyde, tosylamine were treated together to form the Schiff's base. The initial step is the formation of the Schiff's base. Once the Schiff's base is formed, this is treated with the magnesium bromide. The corresponding Grignard reaction leads to the cyclization or the addition reaction at minus 78 degree. This reaction is carried out. So this actually the methyl magnesium bromide adds to this particular carbon, and then we end up with this particular intermediate. So this was subjected to Hofmann-Loeffler reaction. So here the oxidizing cyclization using iodine is carried out. So we end up with a cyclized derivative, and then the detosylation actually is carried out using sulfuric acid, and that also followed by the removal of the methoxy group takes place, and then the N-methylation reaction is carried out using Eschweiler-Clark reaction. That means formic acid formaldehyde combination leads to the N-methylation. So by that we end up with the corresponding nicotine, plus or minus nicotine. So this is actually the chiral center. Let us look at some of the medicinal importance of alkaloids. We will look at nicotine, hygrine, quinine, morphine, cocaine, and reserpine. So the nicotine, when we talk about this, is actually being explored for the pain relief and treating obesity, to reduce schizophrenia effects, and it is also used for treating Parkinson and Alzheimer's disease. So this also helps to treat addiction to or the dependence of smoking cigarettes. Of course, nicotine is present in cigarettes, tobacco plants, but this is also used for the treatment of addiction. And this is also used as a sedative or a stimulant. So when it is used as a stimulant, what it does is it actually makes the adrenal gland release adrenaline, and it also causes release of dopamine. So the release of dopamine happens indirectly. So these two reactions, the biological reactions, are very important for the stimulant nature of nicotine. And nicotine also acts on neurotransmitter receptors, and during this process it actually alters the electrochemical properties of variety of synapses, which in turn actually affect the release of several other neurotransmitters. So that means this is a cascade effect or a multiple effect. So nicotine directly affects few neurotransmitter, which in turn affect few other neurotransmitter, which in turn affects other neurotransmitters. So that means we have to be very careful in handling or using nicotine. The next one is the biological effect of hygrine. Hygrine is generally used as a anticonvulsant, and this is having more negative effects. For example, hygrine affects the central nervous system, especially the neurological disorders in which the brain activity becomes abnormal is caused by hygrine, and hygrine also causes seizures or a period of unusual behaviors, sensations, and sometimes loss of awareness. So that means this is also having a very negative effect on the human health. Let us look at the medicinal importance of quinine. Quinine is a medication that is used to treat malaria and babesiosis. So, these are all the two major diseases which are treated by quinine. This is also used to treat lupus and arthritis. Some of the common side effects of quinine include headache, trouble in seeing and sweating. Of course, some of the major side effects include deafness, low blood platelets and irregular heartbeats. So, we have to be very careful while we consume quinine. So, large amount of quinine consumption leads to lots of side effects. The medicinal importance of morphine. Morphine is basically a opioid medication. It is obtained from opium plants, so it is a opioid medication and it directly affects the central nervous system. So, if you look at various alkaloids, they generally affect the central nervous system. Thereby, they affect the emotional responses to pain, especially morphine reduces the pain. So, that means it is only reducing the emotional responses to the pain, but it does not actually reduce the pain. So, this sometimes behaves like it is generally given as a sedative or anesthetic during operations also, and mainly in many pre-operative conditions this is used to reduce the anxiety, or it may also help in the sedation process. To facilitate the sedation, morphine is also given during the operation. Prior to the operation, the patients are given morphine. This is also effective in relieving the pain caused by myocardial infarction, labor and cancer. Because when a patient is suffering from cancer, morphine can also be given to reduce or to alleviate the pain caused due to the cancer. It may also help in reducing symptoms of shortness of breath due to both cancer and non-cancer causes. But this is also having some negative effect. The negative effect of the morphine is like consumption. That means if you start consuming a lot of morphine, that leads to constipation, some hormonal imbalance in the body, and some minimal impairment of human performance on sensory, motor, attentional and cognitive activities. So, we have to be very careful. And let us look at the medicinal importance of cocaine. So, it is generally used as a local anesthetics or a numbing agent, and this is also used as a stimulant. So, some of the negative effects of the cocaine include the potential cardiovascular toxicity, glaucoma and pupil dilation. So, these are some of the negative effects of cocaine. As a stimulant, this actually leads to increase in alertness. So, feeling of well-being and euphoria, increased energy and motor activity and increased feeling of competence are some of the stimulant effect of cocaine. So, that is the reason you can see in many artists generally take cocaine to use it as a stimulant for their performance. Cocaine is also known to have a number of deleterious effects during pregnancy. And let us look at the medicinal importance of reserpine. Reserpine actually lowers the blood pressure, so this can be used to reduce the blood pressure, and it is also used to treat agitated psychotic conditions such as schizophrenia, and it is also used to treat hypertension, especially under high blood pressure conditions. It helps to prevent strokes and heart attacks and kidney problems in aged people. And some of the side effects of using reserpine include drowsiness, dizziness, tiredness, nausea, vomiting and diarrhea. So, care should be taken while using any of the alkaloids as a medicine. Let us recap in the summary what we have studied so far. We have studied the structural elucidation of hygrine. So, what is the molecular formula of hygrine? How many quaternary nitrogens are there? Whether it contains a carbonyl unit? All those things we have studied. We have also studied the synthesis of hygrinic acid and hygrine separately. What is the biosynthetic process by which hygrine is synthesized from ornithine? We have studied. So these are all the various methods by which the structure of the hygrine is deduced. Then later on we moved on to study about nicotine. What is the structure of nicotine? What is the structure of nicotinic acid? And how nicotinic acid can be prepared from different starting materials. With that, how we can actually deduce the structure of nicotinic acid we have studied. We have also studied about the connectivity, at which carbon the nicotine is connected to the side chain we have studied. And we have also studied about what is the side chain that is present in nicotine. We have also carried out the synthesis of nicotine to confirm the structural elucidation. So later on we studied about the medicinal importance of few alkaloids. We studied about nicotine, hygrine, quinine, morphine, cocaine and reserpine. With that we conclude this session. Thank you.